So hello everyone. How are you doing today? Great day one of PyCon India. How many of you were here for day 0? So a lot of you. This is fantastic. You know, I am so glad to be at PyCon India. This is an amazing conference. I think that this is one PyCon India, PyCon China, PyCon APAC, PyCon UK, EuroPython. I think that those are probably, other than PyCon US, probably the largest PyCons in the world. And so I am so grateful to be here. India is not only just a wonderful country, but you have such a great community here, and I love being here. You know, I have to tell you that PyCon, any PyCon, is actually a pretty special place. I have the chance to visit a lot of different communities, and there's something really special about the chance to be at PyCon. The friends that you make here, the opportunities that you have here. And so since I was given the opportunity to actually be here near the beginning of the conference, I'd actually like to talk for just 1 second about making this PyCon your best PyCon ever. How many of you are here for the first time? Oh, wow. This is great. So I'm going to, before I go into the meat of my talk, I want to give you 3 tips for a better PyCon. And so the first is, number 1, come to contribute. There, at other conferences, there's a sense that the organizers and the sponsors are there to cater to the various attendees. That is not really what PyCon is about. At PyCon, you come to contribute. You come to find ways in which you can serve and help and lift up others. And in doing so, you will find that it will make your PyCon the best you've ever had. Give a lightning talk, participate in an open space. There's the Dev Sprint room. Evidently, the GenSim folks were sprinting all the entire day. I use GenSim. It is a fantastic piece of software. And volunteer to help the organizers. There are people running around doing loads and loads of work for you. See if you can help them. When you are engaged and help others, it opens up the opportunity for you to have a good time. The second thing is meet someone new. I have a lot of friends who I only meet essentially at PyCon, even once a year, but I consider them very, very dear friends. One of the greatest things about PyCon is something we laughingly call the hallway track, because there are 3 tracks of speakers, and then there's a 4th track out in the hallway where you're finding out about new things and you're talking with people and you're having some of the best conversations you've ever had. Make sure to meet someone new, engage with someone. There are conversations and new things that come up simply because you happen to be standing next to each other in line. I was out in the queue for lunch, and it was a great queue because I got the chance to have a really great conversation while I was there. You too can have the same thing. And the third thing is I want you to make sure that you say thanks. There are speakers who have volunteered their time to come talk to you. There are organizers who have been working and meeting for months and months to try and make it possible for you to be here. This is being grateful is key to who we are in the Python community. When you notice someone who is doing the work for you, make sure to say thanks. Make sure to be grateful. I want to personally thank many of those who have been helping me. Anuvat, Shyam, Sahil, Vipin, let's see. I know I'm going to forget some of them, many others, but they have been there helping me, and I want them to know I appreciate it. I also want to mention one other thing, that it's important that we observe the rule of 2 feet and 2 hands. At a conference of this size, not everything is going to be perfect. But if you don't like something, if you don't like the place where you're at, the rule of 2 feet says, walk someplace else, move someplace else, go to where you're going to have a good time. If you see something that is wrong, the rule of 2 hands says, go and put your hands to fixing it. If you do that, then you'll make sure they have a good time. So now, with that, I'd like to turn the time to sort of my primary topic today, which is failure. Now, as much as it seems that I just wanted a chance to look up a bunch of silly memes on the internet, and believe me, while I was preparing this, I did. And it also seems, I thought, well, I should really pick a topic that I'm really excellent at. This is something that I have extensive experience in. And it's true, I really, really do. But the source of this topic actually came from a conversation that I had not too long ago in a train ride going from Bristol to London in the UK. And I was talking there with somebody. He was a civil engineer who just started to do software. And he was learning more and more about software, and he said, why is software engineering even a thing? Why is it a discipline? He said, when I'm doing engineering, and I may use math, and I may use calculus, but I don't say, I am doing maths, I am doing calculus. No, I say I'm doing engineering because that is the thing that I'm doing. That is the thing that I am accomplishing. And it struck me that that was actually not a bad question, because intrinsically I thought, well, software engineering is a thing. I have been a software engineer for 15 years. I've identified with it. I've worked at it. How could software engineering not be a unique thing? But I wanted to, I wanted to say that he actually had a point, though, because I don't really focus on the things that sometimes I focus on the things that I'm trying to solve. And there was a great quote by Patrick McKenzie. I don't know how many of you read Hacker News. He's Patio 11, where he wrote this whole article about saying, don't refer to yourself as a programmer or a developer or a software engineer. He said, people find value in different things. Identify the thing that you do that provides value and say that that's the problem that you solve. And this was very similar to what my friend here on the train suggested. He said, the thing that I do that provides value is I build buildings. I build bridges. That's how I provide value. I do the software to that. And I thought that it actually made sense to think about why is what we do a thing? And ultimately, I thought software engineering is a unique discipline because of the ways in which we fail. Now let's think about for a second, what is an engineer? Well, historically, an engineer was very similar to a craftsman, somebody who would work with their hands building and designing complex machines. Now, I think the very earliest uses of it had to do with siege engines, giant war machines that people would use to attack castles and things like that. As the world started to get a little bit more complicated, you started to have people talk about their specific type of engineering, the type of system or mechanical thing that they specialized in. You got railroad engineers and steam engineers and civil engineers. And so when you would ask them what they would do, they would be able to point to the specific item that they had, and they would say, this is what I built, this is what I maintain. Their identity as an engineer was intrinsically tied to this thing that you could talk to. Or in other words, you could say that they were defined by their purpose. They were defined by their ability to change and move and create a specific sort of system or a specific sort of machine. Well, we can appreciate that because we know what a railroad engineer does because we can see the railroad, we can see the steam engine. We know what a civil engineer does because we can see the buildings. But Then along came software. How many of you have taken a look at software recently? Like physically, what's it look like? I mean, to a certain extent, there's no there. I mean, we use the language of building and architecture for software. We talk about, sometimes when there's an issue, we talk about breaking the build. Or we talk about software architects who create these relationships among different things. But on the other hand, there's this problem that we don't actually, there's no there. I mean, we're talking about an arrangement of electrons and magnetic potentials, sometimes on a disk, that may or may not exist. I mean, and then what's more, sometimes we use the language of artists or artists to talk about what we do. And to the extent that we create intellectual property, we create copyrightable intellectual property, which is the same sort of thing that artists or authors would do. And we talk about authoring software. So we're not exactly the same as engineers in that way, in that we say that this is a creative endeavor. And then we go further in that we create and destroy our creations every single time we push a button or we turn on a computer. We build up these mountains of architecture, these mountains of software, and destroy it and build it back up again. There's no permanence to what we do. I think that there's a funny quote that says, if we built software the same way that we built, or if we built buildings the same way we built software, then the first woodpecker would have destroyed all civilization. And you all laugh because you know that it's true. There's something unique about software where it's defined both by its permanence and by its impermanence. We also, the last talk in here was also about AST hacking. And there was a comment that, well, the use case for ASTs is of course in compilers, and the world runs on compilers that day. Have you ever thought about what a compiler does? Well, a compiler takes all the stuff that you so painstakingly architected in a particular way, and it strips out as much of it as possible and compacts it into a binary representation that the computer can understand, and the computer is really, really stupid. And good compilers will even find all the different pieces that they are able to completely strip out of your program. So something that you thought was really, really necessary might not actually even be in there because the compiler thought, So this is where we are with software. But yet, what makes software engineering a discipline? It is particularly that different set of constraints that allow us to fail in so many different ways that make software engineering. In particular, I don't want to talk about in literally all the different ways to fail, because there are an infinite number of ways to fail. And there are only a smaller number of ways to get things right, but the ways you can fail end up being kind of a signature. And so in particular, what do I mean by failure? And I think that this really comes down to, when you think about it as a class of failures, there are really two major things. The first thing is not accomplishing the thing that you want to do. If you don't get it done, you failed, period. The second one is, well, what if you do the thing that you want to do, but you do a bunch of other stuff as well that may not have been exactly what you want? Well, that's also a type of failure. Of course, you can win the lottery or hit the jackpot, whatever you like, and you can get both types of failures at once. You can not accomplish your goal and cause a bunch of mess to happen. I know I've done that many, many times myself. It is a great way to fail. But I want you to understand that even though there are many ways to fail and only a few ways to get things right, it is hard to talk about all the different ways to get things right because that really ends up being specific to the problem that you're trying to solve. If you think about my friend, he said, I'm trying to build this building. I am trying to build, this bridge. Other types of engineers will say, well, I'm trying to build an airplane. If you built an airplane when what you really wanted was a bridge, that's a failure. And so really, there are so many types of the success is specific to each problem. But failing, you can talk about that in generalities because anytime you don't get exactly what it is that you want, failure is basically the opposite of success, and not even that. So let's think about why we fail in software engineering. And I've thought about this for a long time, and it turned out that there were, to my mind, 3 main causes of failure. And the first is something that I would think about as a failure of the tools or our understanding of the tools. For example, this would be syntax failures. If I can't get the program to compile, I've failed. If I use the incorrect API or I call it the wrong way so that I get a blue screen of death or something happens, I have failed. It's also possible to have strict capacity problems. For example, if I try and allocate a gig of memory and I've got a microcontroller that's got 512K, I'm going to fail. Sometimes there are just hard physical constraints that say, this tool is not exactly made for this particular type of problem. And that's okay, that's a type of failure. Now I want to be careful talking about constraints, those physical constraints, because sometimes those are self-imposed and sometimes those are just hard physical ones. I'm talking about the hard physical constraints here. The second thing is looking at failure to model the world correctly. Now, what do I mean by this? Well, it turns out that software isn't quite so impermanent, or at least it doesn't necessarily need to be, because we hook software up to devices in the real world and we make things happen. In the UK, right now, they are distributing to every 11-year-old in the entire country a tiny little $5 computer called the microbit. Now, what is, among other virtues that this little thing has, is that it runs Python. And so you hook it up via USB to your computer, and you open up a shell, and you can say light.on, and when the LEDs goes on. And you just made something physically happen in the world. And I tell you, it blows these kids' minds. Because they can make that light blink. And what's more, they can make it blink when they press a button. Have you ever seen anything so cool as that? More concretely, scaling a little bit up from that, several years ago, they lost a Martian lander. A bunch of scientists lost the Martian lander because they had 2 teams working on it. One was a team, I believe, from the EU, and one was the team from the US. And one used metric measurements, as God intended, and one used imperial measurements. And they forgot to properly account for the difference in measurements when they converted in the software. And because their software did not match the physical model did not model correctly what they were physically doing, it went someplace and they don't know where it went. They lost it. It was a failure because they didn't model the world. A month or 2 ago, Tesla, their autopilot software, had a failure where they ran full speed into a truck. And the reason why, they said, is because it was unable, in that particular set of lighting, to distinguish between the white side of the truck and the sky. Their model didn't fit the world, and it caused very real damage. Failure. But now we get to this tricky little piece where we can also cause different types of failure because we don't think about something correctly. Now, the other two previous sources of failure we share with other types of engineering disciplines. Other engineering disciplines can use their tools incorrectly. They can misunderstand what to do. Their tools can fail. They can improperly model the stresses on a particular span in a bridge and have it crack or something like that. But we have a particular set of failures that are unique to software. And it comes from this idea that we are building up and tearing down giant logical abstractions in the computer and in our head all the time. And if we don't think about those things correctly, we will fail. Now, these sorts of failures are algorithmic failures. They're failures where something may represent the real world completely, but it does not necessarily comport with the time and space constraints that are imposed by the mathematics. Now, you don't really hear about this from other people. I mean, engineers don't worry if their math is mathematically correct. I mean, it just is. It's the tool. But as software engineers, what you are doing is you actually create mathematical relationships in your code when you create something new. You need to make sure your math is mathematically correct. And if you don't, you can fail. Returning to my conversation with my friend here in the train, that actually had a great way of illustrating all three of these possible methods of failure. I said he was a civil engineer, and the reason he was getting into software was so that he could model in 3D the various pieces of his bridge and represent them on screen. So let's think about not using his tools correctly. Failure of skill. If he incorrectly called the OpenGL API, it would fail. That's failure mode 1. If he didn't model the structures correctly, so it didn't represent what he was actually trying to do, that was failure mode 2. But assume that he was able to model the real world correctly and model it in a way that was syntactically correct. But he had an exponential algorithm where he was trying to go over things in such a way that it took so much time and space to compute that it didn't work. That would be failure mode 3. And it is the combination of these three types of failures that define software engineering. Now, I want to, it may be so surprising that I'm so positive about failure. And like I said, it could be just because we talk about what we know. But I really think that failure is an important part of growth. How many of you have had the chance to use continuous integration tools? Go ahead. Why do you use continuous integration? Someone's just yelled something out. Say again? Fast feedback. Feedback in case of what? In case of failure. You're trying to find out how fast you fail. Because that is the thing that teaches you where you did it wrong. In fact, if any of you think about test-driven development, the very, very pure classic test-driven development is, you could really call it failure-driven development. Because you write the test case, you watch it fail, and then you write the code to make it not fail. It's failure-driven development. You're eliminating failure. And you use the tests in order to help you know that you are thinking about things correctly. There's a great quote from the book Ender's Game. I don't know how many of you have read it, but let me read it directly to make sure I get it right. It says, "There is no teacher but the enemy. No one but the enemy will tell you what the enemy is going to do. Only the enemy shows you where you are weak. Only the enemy tells you where he is strong. The enemy is more clever than you. The enemy is smarter than you. And from now on, you are always about to lose." Failure is the enemy. And only failure teaches us what we need to know. And I can guarantee you that failure will always be there, right within our grasp. Because, there's a great saying about making something idiot-proof. As soon as you think that you've made something idiot-proof, the universe comes along with a better idiot. And I guarantee it's true. Many times I am that better idiot. I'll tell you. And so what we need to do is, instead of talking about all right, we fail, we say, what does this force us to do? How do we change? And in particular, failure, either in response to something we observe in a test or a bug, or even the process of creating software, is a response to failure. Growth is a response to failure. One of the magnificent things about software engineering is that we can use our creative capacity to write things into existence that change the world, that have physical capability. That is a power beyond anything that people had in years and years ago. And you do that because you perceive a failure in the world. Something is not happening the way that you would like. And so you can create and build a system simply by thinking about it and writing it down in such a way that these marvelous tools that we have interpret what you say and they make it exist. That's astounding. That is what we do as software engineers. But, as we said, failure always comes. So how do we deal with failure? Well, there's a lot of ways. First of all, we change. But I think that there are 3 ways that we really need to think about dealing with failure, and they correspond to these different failure modes that I talked about earlier. The first is, if we use something wrongly, if we don't understand our tools, we increase our capacity and our skill with those tools. This is straightforward. This is a lot of what we're doing at this conference. We are becoming better, richer, more able people, more able to solve problems through the learning that's going on here. I think that the second thing is, this has to do with understanding the modeling of the world. If we don't correctly understand the physical reality or even the social reality that we are trying to model, then we need to increase what's called our domain knowledge. We need to understand the correspondence between what we are creating in software and the thing that we are trying to affect outside of the software, and make sure that those 2 things more closely correspond. That's what I mean by increasing our domain knowledge. And the third one is that because we can fail by not thinking clearly, precisely, and correctly, we need to practice the way in which we think. If we do not think correctly, we need to identify the errors in our methods and systems of thinking. And only when we do that can we make sure that the things that we talk about and the things that we write down and the things that we create with our minds and our hands are correct. So we also have skills that we talk about for avoiding failure. I mentioned earlier continuous integration. This is simply one of the tools, but these are things that Python actually ends up being particularly good at. How many people have typed import this? If you haven't yet, you should. It's one of the most beautiful pieces of prose I've ever heard. It's called the Zen of Python. And one of the things that it says is that it says explicit is better than implicit. And I've found that that is a good rule of thumb for anything in my life. A lot of these failures come about because, not because of what I knew, but because of something that I thought was true and just wasn't. You need to make your assumptions, the things that you think are true about the world, you need to write them down, because the process of writing them down allows us both to examine them and allows us to test them. The second thing is that we test our assumptions. Once we have written them down, once we understand there are new inputs, there are new things that we are going to bring into, that we're bringing into our system that may not be explicitly accounted for, or at least are now explicitly accounted for, we need to make sure that those things are true, or at least that they are true enough under the circumstances that we are using them in order to handle it. Now, I said some weird words right there. I said they are true enough. A lot of times, what we're dealing with is not absolute truth with a capital T. We're dealing with, does it work in this particular circumstance? And so this is one of the ways in which we avoid failure, is by saying, is this assumption true in this particular case? Is it something that I can work with? Is this something that I can represent that it is good enough for my purpose? That is what duck typing is about. It's good enough for the purpose right now. All right, we can use it. We can move ahead. Sometimes you test your assumptions up front. Sometimes you test them in the moment. But make your assumptions explicit and test them, because otherwise you have a hidden source of failure. And finally, and this is very, very important, we need to embrace change. That means that when we find that any of these things that we have identified, either an assumption is incorrect, or we found that after testing it that it is incorrect in this particular point, we are not going to get better, we are not going to be able to have success, as we've defined it, unless we do something to deal with that failure. And that, of necessity, means change. In the simplest case, and I hope you never do this, you can write accept, pass. Half of you laughed. That's okay. And just go on. More often, what you need to do is you need to understand there's something new that came into my world, evaluate what it is, and represent it so that you have a better model of either what's coming in or what's going out. So now I'd like to talk for a second. It occurred to me that the things that I was talking about in terms of software failure also applied to me personally. Well, like I said, I have lots and lots of experience with failure. And it seemed to me that a lot of the ways in which I personally fail came down to actually some of these same problems. First is a failure of capacity. A lot of times, I'm just not smart enough. I just don't have particular skills or capabilities. One of the things I've been trying to do is I've been trying to get a little bit more fit over the past year. I've got some physical fitness goals that I just haven't hit because I just don't think I've got the capacity right yet. But I'm working on it. But that is one aspect of failure. The second thing is that a failure to model the world. It's not just understanding the world, but a lot of my failures come come from a failure to correctly understand what's going on inside of other people's heads. And we have names for this type of failure. They're called cognitive errors. And there's a whole list of them, or cognitive fallacies also. Also, if you go to Wikipedia, there's actually like a massive list of like 42 different ways in which we can incorrectly think about others and think about the ways in which they process information. I'd like to bring up just a couple. First, this is one that bites me all the time. I always assume, essentially, that people can read my mind. Because if something makes sense to me, obviously it should make sense to you. You're a person too. You're intelligent. You can... But we don't take into account the particular context that we bring, the particular background that we bring. And so we assume that even without necessarily saying something, people understand what we mean. And when we don't, we're disappointed, and we're disappointed, and we frequently have failure. This is one of those ones. Remember how I talked about dealing with failure meant making our assumptions explicit, making the things that we know explicit, the things that we care about and want to have happen. It's the same thing. The third source of failure, remember how I said it was a failure to think correctly, to understand algorithmically what was going on, the relationships within our own head. Well, that can happen all the time too, except with a failure to know ourselves. If we do not evaluate our feelings, our capabilities, our thoughts, if we don't aggressively introspect, then we are likely to be falling into some of those same fallacies. Because the failure to misunderstand others could also be equally a failure to misunderstand ourselves. It's just they're two sides of the same coin. I've got a dear friend who many times nothing is ever this person's fault. I really like him, but nothing is ever his fault. I don't know how many of you have ever met somebody like that. It was always something else that happened. Another person thought this, some unfortunate thing happened. And that failure to accept responsibility is, I think a lot of times, yes, sometimes legitimately things happen, but a lot of times it's just failure to really understand what was going on inside of his own head. And to understand that sometimes he wasn't quite thinking about it in the correct way. So, we deal with personal failure in the same way we deal with software failure. We change. But I want to focus on one thing for a moment. Notice that I have not said a darn thing about fault. Whenever there's a failure, almost always people talk about, well, it was his fault or her fault or this fault. It was the fault of this thing. Nah, failure doesn't care. You failed! But let's think about this in a software engineering context. One of the things that I work on regularly is distributed systems. Anyone have experience in distributed systems? A couple people? One of the tough things about distributed systems is that you've got different things going on at the same time. They're concurrent. But also, because you cannot accurately represent the internal state except by messages between different pieces of your system, and those messages can be lost or garbled, it is difficult to reason about the system as a whole. And what's more, the chance that you are going to lose some important message goes up a lot with the number of different parts in your system. And so when you are dealing with very complicated distributed systems, well, the chances that you're going to miss a message or you're going to get one that's garbled or one that is even actively incorrect goes almost to 100%. There's something called Byzantine failure where you try to check and recheck and go back and forth with each other. Ultimately, it doesn't really work. Because what you need to do is you need to say, I accept that there may be circumstances beyond my control where I may receive incorrect messages, incorrect stuff may happen, or not just messages, the server might just explode. I've literally had a situation where a car drove into the generator on the side of the data center, and it caused a whole bunch of stuff to go down. It isn't just something that people talk about. It has happened. So that is absolutely a failure. Things are going to stuff is going to happen. But that doesn't necessarily mean that the system that you are thinking about and the system that you are working on needs to fail. It is not anyone's fault that a particular server went down. It simply is. But what we can do is we can engineer around it. We can accept the world as it is, and we can think about ways in which we can have backups, the ways in which we can deal with failure, small failures, gracefully, and still accomplish our purpose. This is true both in software and personally. I'd also like to address one last thing. Responding to failure is more than just, responding to failure is not necessarily a moral principle. I believe that it is part of many moral systems, but I'm not talking about those today. But I'm talking about, this is about good engineering. And good engineering both applied to our systems and to ourselves. Software engineering is increasingly becoming the key skill in the entire world. Many of you have probably read Mark Andreessen's, or at least heard of his op-ed in the New York Times, where he said, software is eating the world. Software is what you are doing. It is the most important thing, and will be, in the future. Because more and more, the ability to create systems simply by thinking about them and by writing them down is so much faster and so much more efficient that it is drowning out every other form of intellectual property. And intellectual property, in particular software-driven intellectual property, is driving out every other single form of capital in business. This is the future. And so, if we want to be in that place where hopefully a woodpecker doesn't cause our future skyscrapers and systems to crumble, take responsibility for dealing with failure, because they happen. Find out ways to deal with them gracefully. And sometimes, just sometimes, if we deal with software, if we deal with failure gracefully enough, we can succeed. Thank you.
We don't have a lot of time. Stick around. We've got a few announcements. We've got time just only for one question. So, is there somebody who would like to ask something? One quick question. Please close the door. No questions? None at all?
All right.
Okay.
Thank you all.
All right then. Thank you, Van.